Well, geometers, it's time for the home stretch of our course. The home stretch of our course takes us through transformational geometry. Um, the key here is Klein's Erlanger program. I don't believe there's an E at the end of that. Klein's the guy who basically posited that all geometry is projective geometry. I don't prove that two figures are congruent because I can pick one up and put it down. I prove that two figures are congruent because I can perform a series of transformations that turn the one. I can project the one onto the other. That's his basic notion. It allows us to bring a few areas of mathematics together. There's a lot of intuition, and so we want to define what a transformation is. A transformation is any bijection that takes all of the points in the plane to all of the points in the plane. The domain and the codomain are each the entire plane. A transformation is any bijection from the plane to the plane. We often think about transformations as moving these three vertices of this triangle to these three vertices of that triangle, but really to do that, the transformation has to move every point in the plane to some other point in the plane. Domain and range are both the plane. A transformation is called an isometry if it preserves distances. And so these are the ones we focus on in our study of transformational geometry. These are the ones that matter for every pair of points A and B. The distance between the image of A and the image of B under this transformation is the same as the distance between A and B. So isometry, that's two Greek words. This is same, and this is measure. Iso from isosceles, same. Metros from pretty much everything metric, measure. Specifically, the identity function I from the plane to the plane is defined by I of P is equal to P for every point P. So the identity function is the function that takes nobody anywhere. It leaves everybody in place. Some things we should know about isometries. The composition of two isometries is an isometry, and the inverse of an isometry is an isometry. Neither of these are difficult to prove. We assume that T1 and T2 are isometries, then we know that the distance between the image of P under T1 and the image of Q under T1 is the same as the distance from P to Q. And so then we know that if we do T2 to T1 of P and we do T2 to T1 of Q, then that keeps this distance whatever it was before, and whatever it was before is PQ. So that's great. The inverse of an isometry is also an isometry. So you have 2 points. You have the inverse of P and you have the inverse of Q, right? And so if you do the transformation T to each of those points, then the distance remains the same as the distance between the inverse of P and the inverse of Q, right? Like that's, if I do an isometry to both of those points, which must exist in the plane, the answer I get out is the same distance between the original points, but T of T inverse of P, that's just P, and T of T inverse of Q, that's just Q. And so this is the result that we wanted. The inverse of the isometry takes those points to points that are that far apart, and we've got it. There are lots of properties of isometries. Those come in another video. That's good enough for now.